What is up, mathletes? Welcome back to another episode of Math with Dr. Math, and today we're going to talk about that remainder theorem. Don't go anywhere. Alright, so let's talk about that remainder theorem. It's kind of a deep dive here, so let's go slowly and let's make sure we explain all these ideas. Alright. So I have the remainder theorem here, and of course we're going to be looking at polynomials. And here's the understanding. Here's the basic idea. All right, we're going to have some polynomial, and we're going to divide it by a binomial, and the binomial has to have this form: x minus some constant, we'll say a. It could be a fraction, it could be a square root, it could be a radical, any type of radical, right? As long as it's a real number, all right? And the remainder is going to be obtained. You could do long division, you could use synthetic division, but you could also just plug in this value of a into your polynomial, and that'll give you your remainder, all right? So at first, these ideas and these definitions, they seem very abstract, right? So let's look at some examples so you can see what the heck is this telling me. Because right now, most of us feel like this guy.
Bad idea. That's a very bad idea.
All right. So let's look at an example, but we'll do a few examples here so you get more and more comfortable. All right. So let's look at this polynomial p of x. And it's x cubed minus 4x squared minus 7x plus 10. And what we're going to do is we're going to divide it by x minus 2. And so according to my remainder theorem, right, my value of a here is 2, right? Because it's x minus, it's already in the form x minus something. So my a value, right, is 2. So the remainder can be determined by finding p of 2. And right now you're like, why do I even need this? Well, we're going to see as we move through this chapter, we're going to see that this is a very powerful tool. But just like anything, you have to be comfortable with using this tool before you start applying it to all these places, right? We got to get the process down. All right. So what this is saying is if I plug in 2, right, this value here, everywhere I see x, and I evaluate that function at 2, well, this answer, right, p of 2, the output, the answer here, this is going to represent the remainder of, if I were to take this function and actually divide it by x minus 2, this is going to be my remainder. And as we move forward, we're going to have one remainder in mind because this is going to lead to so many, I'll call them shortcuts, all right? But again, we first have to be good at using this before we dive into those ideas. Here's some background. So before we proceed, some things we need to recall, all right? So if we have some polynomial here, and it's just a picture of a polynomial, remember the zeros are where the heights, right, where f of x, if this is a function f, is equal to 0. So basically our zeros, that's just another way of saying my x-intercepts. A lot of people don't make that connection, and so as they move forward they end up really lost. So just real easy, zeros, that just means our x-intercepts. So what that means is if I have this function and if I plug in -2, my x-intercept, all right, sorry, this is an x-intercept because the output is 0. When I plug in 1, I get an output of 0, right? Meaning this is also an x-intercept, it's a 0. And when I plug in 3, right, I also get a 0 because my output is 0. So what is that going to tell us? Well, notice what that remainder theorem says. If I plug in some value, this output is going to give me my remainder. So what I'm saying is whenever you get an output of 0, what that means is that you have really found a x-intercept of that polynomial. All right. So again, all of these words, what the heck does it all mean? So let's now dive into some examples. So let's start by making sure we know how to use this theorem properly. All right, so we're going to use the remainder theorem here to we evaluate the polynomial for the given values of x. So here, you're going to be given two values of x. And what we could see is if we get 0, then we know we found an x-intercept when we plug this in, right? And this, again, where we're moving, I can't say it enough how helpful this is going to be to us. All right, so let's go ahead and let's use this remainder theorem. So remember what the remainder theorem says. The remainder theorem says is you give me an input, right? In this case, it's -1. So if I take that original function, k of x, that hopefully you copied down, if not, rewind, all right? If you take k of x and if you divide it by x minus -1, right? That's what the theorem says. If you divide it by x minus a, in this case, our a value is -1. -1. Well, check it out. A negative and negative is a positive. So when k of x is divided by x plus 1, right, because that turned into a plus, then the remainder is whatever we get when we enter in -1, all right? So there's going to be two ways that we could find, actually three ways, right, that we could find the remainder. Today we'll just be talking about two of those ways. So one way is you could actually plug in -1 into the original function, but here I want to show you using synthetic division, right? So if we use synthetic division using this input of -1, right, let's see what our remainder is. All right, so we took all our coefficients, right, and we listed them. And again, if you don't know what synthetic division is, I have a video linked down below where we talk about how to use synthetic division. All right, so that first coefficient, you drop it down and you get 2. Then you multiply -1 times 2 and you get -2. You go ahead and add these two and you get 3. You go ahead and multiply -1 times 3 and you get -3. You add these two, you get -22. You multiply -1 times -22, you get +22. You add these, you get -5. You multiply this times that -1 and you get +5. And then you add these two and there's our remainder. So just a little recap, when you're moving this way, you're adding, right, these constants. You're adding these constants. But when how are you using these guys? Well, you're multiplying all these numbers by whatever is here, right? So whatever your a term is. So -1 times 2, bam. 3 times -1, that gave us this. -22 times -1, that gave us this. But again, watch that video linked below if you have questions about synthetic division. All right, so what does this tell us? So therefore, by the remainder theorem, when I plugged in -1, right, that's what this was, my remainder is 15. Right now, that's all it tells us. Later on, it's going to tell us a little bit more, but for the sake of this video, that's all we're getting comfortable with. We're getting comfortable with just finding the remainder when they give us some input, right? That's it. All right, let's do another example. All right, so now let's plug in k of 2. All right, so when we plug in k of 2, right, when we plug in 2, I should say, that's the same thing, according to our remainder theorem, that's the same thing as us taking that k of x and dividing it by x minus 2. Again, we're dividing by x minus a, but in this case, our a value is 2. So we're dividing that k of x by x minus 2. And what does that produce when you do that division? Well, when you divide this is going to give us our remainder. And another way of getting that remainder is just simply plugging in that 2. So I want us to be, I'll call it bilingual here.
Come again? You know I don't speak Spanish.
To know that, you can use synthetic division to get this remainder that we're going to see in a few seconds, or you could just plug in 2. All right, and we're going to see how much time this is going to save us moving down the road here. All right, so let's go ahead and do this work. Let's use synthetic division. So once again, I list all my coefficients. All right, and let's get to work. So this 2, I drop it down, and then I multiply, I get 4. I add, I get 9. I multiply by that 2, get 18. I add these two, I get -1. multiply by 2, I get negative 2. I add these two, I get negative 29. I multiply this by 2, I get negative 58. And I add these two, and I get my remainder. And again, that's for right now, that's all we're interested in. All right. The whole point of this video is just to show you how to get that remainder using the remainder theorem. All right. So this is kind of the how-to, and later on, what we're going to see is, you know, how is this really going to help us? Because right now, a lot of us are looking at this kind of like she is. So maybe this is a little bit more helpful for us, okay? Because now we're moving in, well, tell us more about when we would use this or how this might be even helpful. All right, so what we're gonna see is, we're gonna get some ideas either by looking at the graph, or sometimes we might have some difficult polynomials to factor, and we're gonna see how this theorem is gonna actually make factoring much easier, all right? So let's say we have this. So we want to use the remainder theorem to determine if some number c, so we're going to take some number and we want to see if this number is actually a zero of our polynomial. And let's say we don't want to actually graph this polynomial, okay? So here's our polynomial p of x, which equals 4x cubed minus 14x squared minus 20x plus 70. And what we want to do is we want to see if these values of c, right, if I were to plug them in, can I see, right, how am I going to know if these are actually zeros of the polynomial? Like, how do I know that? Well, according to my theorem, right, that if I plug them in, and if they are zeros, then what I should get, what does that mean if they're zeros? Well, that means if I were to plug in negative 2 into my function, what I'm looking for is I'm looking to see, is my output equal to 0? Just like that graph we looked at earlier, right? Because that's what it means. If it is equal to 0, what that means is negative 2 is an x-intercept. And likewise for question B, if I were to plug in negative square root of 5 into my function, am I getting a 0? Because if we are, then we know that negative square root of 5 is an x-intercept, right? So now we start getting into, I would say, more useful information here. All right, so let's actually do this. So let's start with part A. So in each case, divide p of x by x minus c to determine the remainder. If the remainder is 0, just like we discussed, then the value of c is a 0 of the polynomial. All right, so you have a choice. You could plug in negative 2, or we could use this remainder theorem to see if we get a remainder of 0. All right, so we're going to divide p of x by x plus 2. So let's grab this x, notice, let me put it in the right form. What we really have here is we have x minus negative 2, right? Because in order for this to be positive, we must have a negative and a negative, right? Because this is the form that we need. So our c value, all right, this c value, earlier we called it a, it's just a number. We don't care what we call it, right? This is what we're going to grab for synthetic division. So it has to be in the form of x minus something. So negative 2, we plug it in for our synthetic division. So here we go. Drop down the 4. We multiply by negative 2. You get negative 8. We add. We get negative 22. We multiply negative 22 by negative 2. We get 44. We add. We get 24. We multiply. You get negative 48. And you add and you get 22. So by the remainder theorem, p of negative 22 equals p of negative 2 equals 22. So what this tells us is that we did not, negative 2 is not a 0. So I'm gonna write that down. Negative 2, right, is not a 0. It's not an x-intercept. All right. So now let's go ahead and check negative square root of 5. All right. So we're going to go ahead and divide that original function p of x by x plus square root of 5. All right, so this is our c value. This is what we're going to plug in here. All right, So essentially, if they ever give you a factor, a potential factor, what you're gonna do, notice I said potential factor, what we're gonna do is we're gonna grab the opposite, right, of this number right here, this constant, and we're gonna put it right here, right? That's gonna be our C value. All right, so here we go. Drop down the 4, then we multiply. So you get negative 4 square root of 5. You add these two. These are not like terms, so we just write it just like that, right? Not like radicals. Then we're gonna go ahead and multiply by negative square root of 5. So when you do that, you're actually gonna have to distribute this negative 5, square root of 5 to both of them, all right? And if you want a video showing how to multiply radicals with constants, just comment down below and we'll work on that video for you. So we're just gonna distribute negative square root of 5 times negative 14. So you get positive 14 square root of 5, and then negative square root of 5 times negative 4 square root of 5, and you get 20. All right, so now we're gonna add these two, this negative 20 and this 20, they cancel out. So you're left with 14 square root of 5. All right, so now you multiply 14 square root of 5 times negative square root of 5, so you end up with negative 70. 70 plus negative 70 equals, boom, 0. So by the remainder theorem, P of negative square root of 5 equals 0. So what does that tell us? Well, what that tells us is that negative square root of 5 is a 0. So what we have found is that this right here is a 0. And that's what we're looking for. So if that's a 0, what we're going to see is later on we're going to be introduced to more theorems that are going to tell us not only did we find a 0, but now we have a factor of this polynomial, and we're going to be able to do so many things moving forward. All right, folks, so that was a mouthful. So don't forget to subscribe, like, let us know what you want to learn more of, and we'll be here to help you out. Peace.